Okay, let's begin. So, had a long weekend. Let's just recap a little bit before we jump into things. Last time we started something called implicit differentiation. So this is differentiating implicitly defined functions. And you can remember what that meant. It meant that your function wasn't explicitly out in the open on one side, like y equals f of x. You had things mixed together. So like x squared y cubed minus 2xy plus ln of y equals 7. Right? So it's like you didn't have your y neatly on one side and all your x's on the other side. You kind of have your x's and y's mixed together, and you probably don't even know what y is, but your y is just some inside function. Right? It's some f of x that you might not know what it is, but you know that's the guy you're thinking of as the function, and the x's are your inputs. But we still want to find, or we wanted to find dy dx anyway. You still wanted to be able to talk about the rate of change of the dependent variable with respect to the independent variable, or talk about the slope of the tangent line, or all that good stuff. And so now the how-to was to just, well, apply the chain rule. And how that was applied here is just apply derivative rules as usual. Right? So your chain rule, your product rule, your quotient rule, the power rule, the derivative of e to the u, derivative of ln u, all of those guys still stay the same, but multiply by the derivative of the inner function when not differentiating the independent variable. So the idea is you'll go through here. So for example, your independent variable is the guy that's identified by putting him on the bottom of the Leibniz notation. So this here tells you the x is the independent variable. Right? So that means, and of course the y is now the dependent variable. So that's the guy who you're going to think of as your inside function. In a situation like that, right? So your x is the original inputs, you're thinking of your y's now as some function of x. And how do you differentiate that? Well, you just do it as normal, except whenever you're differentiating something that's not an x, multiply by the prime. That's basically it. So just to remind you how to do this, I mean, you have problems like this on the quiz, but in case you didn't remember, let's just maybe actually do this problem that I just made up. So how would you go about doing this? Is you're going to go through, you're going to differentiate everybody, and ultimately you want to solve for dy dx or y prime. Now in doing so, your normal derivative rules will apply. So for example, you will notice that the first one can be thought of as a product of two functions, like an f and a g. And so the product rule would apply. F prime times g plus f times g prime. Right? So all the old derivative rules, they still do apply. So now, how is this different? Well, in the case where you're finding f prime, well, that's just 2x times the y cubed plus f times the g prime. So now, in the case of finding the y cubed, however, what you have to realize is that's an inside function. It's some function cubed, and so you need the chain rule. So you're going to differentiate the outer function and multiply by a derivative of the inside. So you multiply by a y prime, or dy dx. And that's basically, that's all that happens there. So once you want to find dy dx, it means when you're differentiating any x's, you don't really have to do anything extra, just apply the derivative rules exactly as written. If you're differentiating y's or anything else that's not an x, you treat it as an inside function and multiply by a derivative afterwards. Similarly, when doing this, you would also use the product rule. So this would just be minus 2y minus 2xy prime. This would be plus, what is the derivative of L and y? Y prime over y, because that would be like a u prime, because we know that the derivative of ln of u is u prime over u, and again, basically that means whenever you have something that's not x, you have to do that kind of process here. Derivative of 7 is 0. And from this point, it's just a matter of algebra, right? So you just want to isolate the guy that you want to solve for, and then you solve for it using algebra, essentially. So on one side, you keep all the guys that have y primes in them. So you'd keep the 3x squared y squared. You would keep the minus 2x. You would keep the 1 over y. And everyone that doesn't have y prime, you move to the other side. So we're going to add the 2y. We're going to subtract the 2xy cubed. That accounts for everybody. And then you just divide both sides by this coefficient. So you can now solve for the y prime. That'll be 2y minus 2xy cubed over 3x squared y squared minus 2x plus 1 over y. Now in general, that's fine for me, but a textbook probably wouldn't write the answer that way because of the complex fraction. They do something like multiply by y over y and write the answer more like 2y squared minus 2xy to the 4th over squared y cubed minus 2xy. So probably see the answer in that form. The other thing that's slightly peculiar the first time you saw it probably was the fact that you now have y's in your answer. And in general, especially when it comes to implicit differentiation, that is okay. You can solve for y prime in terms of both the dependent and independent variables. And we do know that if, in theory, we could solve for the y in the original, then if we plug that into these locations, that would be what the derivative would be had we solve for y in the beginning and just do derivatives the old way. But we did examples that says just solving for y in the beginning and finding the derivative can be quite difficult. In fact, it can be impossible, which is sort of where we ended up. We ended up with one example where we wanted to find the derivative with respect to x. We wanted to find dy dx. But it was impossible to solve for y in the first place. And this was with the folium of Descartes. So we ended with, I want to say it was x squared plus y to the 7th minus 2y equals 3. X squared plus y to the 7th minus 2y equals 3. Yeah, so that was a curve studied by Descartes, Mr. Cartesian-esses, Mr. I think therefore I am. That guy who came up with a Cartesian plane was studying this curve. It's called the folium of Descartes. And if you wanted to, for example, find dy dx, it turns out that you couldn't actually solve for y first and then find it. That was actually impossible not to be, and that's not even a hyperbole, that's like, it's actually impossible to solve for y. But with the power of implicit differentiation, we could actually solve for this, and we did solve for it last time, I'm pretty sure. So let's just go back quickly through this. That would be that, and then I would solve for the y prime by moving that 2x over and then dividing by this coefficient. Right? So that's the answer we got last time. And last time we sort of ended on a note, well, if we couldn't find the y in the original, how is having y in our answer for the derivative going to be useful? And it turns out that, yes, it's still useful. And let me illustrate with an example how it's going to be useful, which is going to give us a twofer, because it's also going to illustrate how a tangent line can be useful, which we'll actually get back to later. So here's one thing we can do. Find the equation of the tangent line. At the point 2, 1. Now, the first thing you want to notice here is that 2, 1 is actually on that curve. It's on the graph. So 2, 1 is actually a coordinate here. You know this is on the graph. Well, because if I plug in x equals 2 and y equals 1, what would happen is I would have 2 squared plus 1 to the 7 minus 2 times 1. That's going to be 4 plus 1 minus 2. That is going to be 3. So I know that that coordinate is actually on this graph. It's somewhere up here. So I can't really tell you what y equals in terms of only x's, but I can tell you a location on that graph. And there are going to be many times in which we can do this. In fact, there's a math class called Numerical Analysis where it has a whole branch that is dedicated to doing this. You have a very complicated function that you can't write around a formula for. Can you find specific coordinates on that function? And it turns out that we know many ways to actually figure out coordinates on that function, and we can program a computer to find them. So while I cannot describe this function in its entirety, it turns out I can pretty much approximate any coordinate along this function that I want. So I can actually talk about this function point by point, but as a general formula, I can't. We don't have the language for it. So assuming that somehow we figured out that this point is on the graph and we actually care about that point, find a tangent line to that point. Right? So there is going to be some line here that I want to find its equation. Okay. Now, how do we do this? This is where you guys come. How would I actually find the equation of that tangent line? Yeah?
Use like the point slope formula.
Okay, we need a point slope formula, but we would need what for that formula?
Slope and a point.
Right, we need the slope and a point. So we need the slope and we need a point. Now the point, we already got that point. x1, y1 is just going to be 2, 1. What about the slope though? How do you get to the slope?
Plug those coordinates into that derivative equation.
The derivative gives us the slope. Remember, derivative was even a synonym for slope. So what we can do is our n in this equation is just going to be y prime evaluated at the point, which is going to give us minus 2 times 2 over 7 to the 1 to the 6 minus 2. So that's minus 4/5. So that's going to be the slope at that point, and then I just use a point slope point. So this means that our tangent line is y minus y1 equals m x minus x1. And that's the equation of this one. So this here is going to be y minus 1 equals minus 4/5 x minus 2. That's the equation of this line. Now, I want you to appreciate the power that comes with being able to do this. So, again, the function itself, impossible for me to have a formula. It's a very complicated function. I don't even know a way to write it down. However, if I have a point of interest, I can approximate what that coordinate would be, and I can get a tangent line there via implicit differentiation. What does that actually allow me to do? Well, remember what a tangent line does. It is a straight line such that if I were to zoom in on this location, the line and the function are going to be doing the same thing. The more I zoom in, the closer together that they would look. So, essentially, it will get to a point where, instead of using the formula for the function, at the location 2, 1, I can instead use this formula to represent the formula for the function. I could solve for y here and use that as an approximation of the function itself. So the function itself, very complicated. Straight line, very simple. I can talk about this and I can study this, and it would be equivalent to studying this at that location. Of course, I have to do it on a point-by-point basis here, but the idea is being able to find a tangent line now allows us to study things that are really complicated using things that are really simple, although it does it on a local basis. So if I were interested in what's going on at this point, well, I can figure that out. Draw a tangent line there, and I can tell you what's going on. What's going on at this point? Well, draw a tangent line there. What's going on at this point? Draw a tangent line there, right? I can figure out locations that are of interest and use tangent lines to study the function at those locations. So being able to draw a tangent line is pretty useful because it allows us to get approximations for our functions. We can use straight lines to approximate functions. And implicit differentiation is useful because not all the time we'd be able to isolate a formula for that function. Sometimes we won't know. And even if we get an answer where the original function shows up, again, if we're doing it point by point, I don't even need to know a formula to find that y. I don't really need to know how to get a specific y. I just need to know how to talk about a specific location. And I can kind of build it point by point. And in fact, as far as a computer is concerned, a function is just a table of points anyway. Like it's going to be useful for all sorts of things. And on top of that, something I want to mention, which is, it's something that's true in general, which a lot of people don't think about it that way because, you know, we're in math class all the time, and it's often the case where it's like, you know, your teacher's going like, no, that's not the answer, this is the answer, it has to be this, exactly this. In real life, a lot of times you can't get to the exact answer. It's not feasible, it's not possible. And an approximation is the best that you can do. And so knowing how to approximate something complicated with something simple is gold, because there are lots of times in life where you can't actually get to an exact answer or an exact formulation of the problem that you're looking at. An approximation of the problem is the best that you can hope for. On top of that, sometimes an approximation is all that you would actually need, because even if you could get to the right answer, sometimes you can't even apply it in practice, right? Most time in practice, you apply approximations, right? If I had to take a machine and cut a piece of wood exactly pi units long, it's impossible. You're not going to know how to cut it pi units long. What is pi? No one's ever written it down in its entirety. The machine has an accuracy of a certain number of decimal places. It's going to approximate pi anyway. So a lot of times you can only implement approximations. Knowing how to deal with approximations is important, and calculus provides a very nice way of dealing with approximations. you can approximate very complicated curves with straight lines, which are very easy curves. And all you have to do is find the location and zoom in, and the more you zoom in, the better your line will be as an approximation. So that's kind of implicit differentiation and the ability of the tangent line to approximate functions, kind of double teaming this problem here. So very complicated function, but I can study it locally using tangent lines, and to find those tangent lines, this is the formula that's going to give me the slope. So very useful. Yeah, there's I don't know how much you guys will have to go into it, but there are entire branches of mathematics devoted to things like this, called numerical analysis is a nice one. It's all about approximating functions. Let's move on to another example. Again, just to tout the benefits here of implicit differentiation. So this is an actual thing here. Let me make sure I write it down properly. So here's a function. Which is not actually a randomly made up function. That formula does mean something. And what if I wanted to find, say, dv dp? Does anyone recognize this formula? Yeah? What is it?
I believe it's where the radius equation. I know what it is, I don't know the exact name of it, but I've seen it before.
Right, so you would have seen it in what class?
Chemistry.
In chemistry, it's in chemistry. Usually you'll study this in Gen Chem 1. This is it's the equation that relates the pressure and the volume of a specific gas. It's called van der Waals equation. Gas. So I wanted to give you an example of a function that, one, you'll notice is implicitly defined. Whether I want to think of P or V as the main function, they're mixed together. So van der Waals came up with this relationship between the pressure and volume of a specific gas, and that's how the relationship presented itself, right? It didn't have like P solved for itself neatly on one side or V solved neatly on the other side. It came as this equation. But you might still want to study the gas anyway. How does the pressure affect the volume? Now, the original equation can tell you how things are behaving at a certain instant in the sense that, oh, I know if the pressure is 1 atmosphere, then, you know, the volume has to be a certain thing. I can actually solve for that. But how would you examine this system in terms of rates of change? If I change the pressure at this speed, at what speed would the volume change? Or vice versa. dP dV would say, if I change the volume at this rate, at what rate will the pressure respond, right? And that can be important, I mean, just to sort of use a crazy example here. So let's suppose someone says, well, if we increase the pressure by 1 atmosphere per second, what's going to happen to dV dP? And if the answer is something like, it'll go to like 5 million meters cubed per second, well, that basically means you have an explosion now, right? You do this, and then poof, that happens, right? So that can kind of tell you what to expect from a certain system in terms of the speed at which that system is going to change. So you can come up with this that relates to volume and pressure, but what if you don't care about volume and pressure, you care about how they react to each other? Now it's a calculus problem. And now you'd want to be able to talk about things like dV dP or dP dV. And how do you even talk about something like that when that's the way the formula comes to you? Well, implicit differentiation is how. So go, how would you find dV dP? And before you're starting, so this is another use of this example, probably what you should be doing at this point is identifying who is your independent variable, who is your dependent variable, who do you think of as the inside function versus the original input? If you want to find dv dt. Yeah?
P is independent and U is dependent.
Right, so this guy is the independent variable, right? So you're thinking of that as the thing you're manipulating. That is the input, right? So this is the independent variable, which means this v is the dependent variable, which means you're gonna think of him as the inside function, right? So by me asking you, what is the rate at which volume is changing with respect to pressure, it's also me telling you pressure is the input, V is the output. So essentially, P is like your X from before, and the V is like your Y from before. Which means, whenever I'm differentiating a P, I don't have to do anything extra, just apply the regular derivative rules. Whenever I'm differentiating a V, I have to multiply by the derivative of V. I have to multiply by a V prime, or a dV dt specifically. So that being said, how would you actually go through and do that in this situation? This is where you guys come in. Yeah?
Do product rule.
Product rule seems like a good idea because I have, again, a product of two functions. This is like an f and a g. So I'm going to do like an f prime times g plus an f times g prime equals, well, the derivative of that, which is going to be 0. So there's going to be a nice little 0 on this side here. Okay, so what would, tell me what the f prime looks like.
1 plus 1 over v cubed, or 5 over v cubed.
Not exactly. How would you differentiate 5 over v squared?
Have these quotient yes.
You don't have to use quotient. Top is a constant. Yeah.
You could
Laura?
It would be negative 10 v.
How are you getting that?
I did 5 times 1 over v squared, and then I did v squared to the negative 1, and then that would be v to the negative 2, and then I brought the negative 2 to
Right,
the
so
coefficient.
this you think of as 5v to the minus 2, right?
Mhm.
So now it's a power rule, it's not really a quotient, it can be easier. So whenever your top is a constant, bring the bottom up, make the power negative, and apply the power rule or the chain rule. If your bottom is a constant, leave it alone, differentiate the top. So we saw that last time. Okay, so now that you're thinking of it like this, what is the derivative?
Negative 10 v.
Negative 10,
V to the negative 3.
negative 3. V prime. You need the dv dt here. Again, implicit differentiation, right? When we were differentiating the p part, we didn't care. He's on the bottom. He's the independent variable. Derivative of p to the 1, you do the power rule. That's just 1. When we're differentiating the v part, the v is the dependent variable. We need to multiply by his derivative. We need to multiply by the v prime. Times the g, which is v minus 0.03, plus f, p plus 5 over v squared, times the g prime. What's the derivative of this?
dv over
dv dp. And that's the first step. That is actually finding all the derivatives. The calculus is done. At this point now, it's an algebra problem. We want to solve for this guy. In which case, what we would do is just multiply out. So, multiply out, isolate the v primes. So, this means take 1 times, you're gonna take everyone in here, multiply everyone there. 1 times v, 1 times that. Then I'm gonna take this times v, which gives you to the minus 2 v prime. So I'm writing v prime here, but it really means dv dt. And then this times that, that's gonna be plus 0.3 v to the minus 3 v prime. Then here, this is going to be p times v prime, and this is going to be 5 v to the minus 2 v prime equals 0. Which means, can't put it here. Let's go. I'm going to isolate the v primes. So that's going to be a minus 10v to the minus 2. And a plus 0.3v to the minus 3. Plus p. Plus 5v to the minus 2. And then the other guy I'm going to move to the other side. So it's going to be a plus 0.03 minus a v. And so my v prime, my dv dp, how the volume is going to change with respect to the pressure is given by this formula. So if you tell me how fast the pressure is reacting, this is the equation that will tell you how fast the volume will react in response to that. And, I mean, you could clean that up a little bit, but it's good. You can multiply top and bottom by v cubed to get that to look a little bit nicer. And you can even combine these two guys here. So those just combine to minus 5v to the minus 2. That's the idea. We'll do a couple more examples of this and deal with a new differentiation technique next time, log differentiation, which was on your quiz. But for now, we'll stop there. It's been a long weekend. Make sure to remind yourself of all the rules and all the stuff that we've been doing because we're going to move forward.